Okay, so let's find out how we can find dA in general given a transformation. And so the idea would be we'd be starting with some region here in the xy plane like this blue curvy shape, and we would say, hey, let's do a change of variables instead to rewrite it in terms of this easier rectangular region in the UV plane. But notice we're changing the area because the blue area is not equal to the green area anymore. And we want to know how we can relate the blue area in terms of UV, DU, and DV. So let's label some things here. We're going to call this area delta A. And this area over here, you can see the green area is just going to be DU, DV. And we'd like to find how we can relate these two. And so what we're going to do is approximate this blue area by something that's the simplest thing we can find the area of, which is just a parallelogram. So we're going to say that delta A is approximately equal to the area of the red parallelogram. And then I'm just going to give you, this is not at all obvious to a lot of people, but I'm just going to tell you how we can find what the vectors are that span this parallelogram. So notice, really what I'm doing is trying to come up with a vector here. And if you notice, that's actually involving how my transformation changes just in U. And so the way we can capture that is actually a partial derivative of the transformation with respect to U. And what I mean by that, it's translating, this green vector right here is going to be the partial of x with respect to U, partial y with respect to U, and then I'm going to scale it times delta U because that's actually going to be the length, how far we've actually gone in a given. That'll help you scale the length. And then this vector here is going to be, the red vector, is going to be partial of x with respect to v, partial of y with respect to v, scaled by delta v. And if that's not obvious, that's okay. This is hard to see, and I just want you to, you can take my word for it at this point, because we're just going to go from here, but it is related to what we learned back in chapter 11 about partial derivatives. Okay, so what we're going to do is find the area of the red parallelogram. If you remember, we can find the area of a parallelogram by taking the magnitude of the cross product between the vectors that span it. So let's take the cross product, and I'll just write it here in terms of a magnitude of a determinant. Okay, so I'm just trying to write this determinant a little bit easier, so I factored out the delta U, delta V, since those are just constants. And then I have these double bars. Actually, it doesn't even have to be double bars because it's just a magnitude. So let's just do that. Okay, so let's calculate this. This is going to give us this quantity here. And this is actually going to be when we take the limit as delta U, delta V goes to 0, when we actually are putting this into an integrand. This is going to tell us that dA is going to become this whole quantity, du dv. And we're going to give a name to the absolute value of this whole quantity. We're calling the inside term, inside here, the Jacobian. And so we'll write that down below. And this is a little bit confusing for people, but just to make the notation more consistent and similar, instead of writing it as this matrix here, we're actually going to write it, we'll still keep the x sub u here, but we're actually going to write it as x sub u, x sub v in the top, and y sub u, y sub v. And notice, when you take the determinant of this matrix, I get x sub u, y sub v, which is the same thing here, minus x sub v, y sub u, which is the same thing here. So it literally means the same thing, but we just write it a little bit different so that it's, I guess, a little bit more easier and consistent with the notation here. This is called the Jacobian of the transformation. And so we'll either denote this determinant by j or this partial. And so I think this is the notation where this is really coming from, because you can see we're doing the partials of x in the top row with respect to u and v, and then the partials of y in the bottom row with respect to u and v. Okay, so this is going to represent the shrinking or stretching of the coordinates that happens from our coordinate change. Okay, and so what does that mean? That means when we actually go and do a coordinate change, let's do a really general one. Let's say that h is g of u v, or excuse me, that x is g of u v, and y is h of u v, so just some functions of u and v. When we go to change from our region R to our new region G, and the whole goal of this is to have a way simpler region G, like up above, it's going to be a nice rectangular green area instead of this more complicated blue. This would be like part of our R, and this would be part of our G. We're just zoomed in really close on these, but okay. So this tells us that the dA piece, one of those little blue areas up above, is actually equal to the magnitude of the Jacobian. And the Jacobian is the determinant of this 2 by 2 matrix. Okay, and then the integrand, we can just replace x in this case is g of uv, and y is h of uv. Okay, so let's go back to the one that we did visually. We already noticed that when we calculated Jacobian in example 1, we got 6. Let's see now how we could do this algebraically and confirm that we also get 6. Okay, so the Jacobian of uv, so notice up above that x is 2u, y is 3v. So the Jacobian is going to be this determinant. Okay, so let's take each of these things. Partial of x with respect to u is just 2. Partial of x with respect to v is just 0. Partial of y with respect to u is 0. Partial of y with respect to v is 3. And so I'm getting 6 minus 0, which is 6. And at the end of the day, if I had gotten a negative value, I would have taken the absolute value when I plug it in. Because again, this is always going to be a positive number. It's representing how the area is shrinking or stretching. And so we'll always take the absolute value at the end. Okay, so let's go to a full example of this now that we have the theory.